Temperature is another really important part about chemistry. And temperature is basically referring to how much hot or cold a substance has, hotness or coldness. Anyway, temperature is related to energy, but energy is not temperature. So we'll talk more about that in Chem 222. But anyway, there's three temperature scales that are very common. The two that we're going to use the most, the first one is Celsius. Celsius was described by that guy Celsius, and anyway, it's in degrees Celsius. A lot of times in chemistry, people will record things in the lab in Celsius and then convert to Kelvin later. Kelvin is used most of the time for calculations, and Kelvin is pretty cool. Notice that Kelvin doesn't have a degree symbol next to it. It's a long story why that's the case, but officially it's degrees Celsius, and you don't put degrees Kelvin. Now, you will see degrees Kelvin, especially in astronomy and in photography, and I don't know why those two fields have to use the improper version of temperature, but you are now hip to the actual things. You're not supposed to use degrees next to Kelvin. You use it next to Celsius, and you use it next to Fahrenheit. Now, Fahrenheit is the one that's used a lot in the USA, just like feet and inches and all that kind of stuff are used. Fahrenheit is used. I will try super hard to not use Fahrenheit at all in this class because it's awkward. I'll talk about it why here in a little bit. But it is used in the USA, and if you listen to the radio or TV, it'll talk about temperatures in Fahrenheit. It won't be Celsius. In Canada and most of the world, they do talk about Celsius temperatures. But so we'll have to talk about some ways to translate from Celsius to Fahrenheit or Fahrenheit to Celsius. But just realize we're going to try really hard to stay away from it as all possible. Why we want to stay away from Fahrenheit is because here's a comparison of the three scales. Celsius and Kelvin on the right and Fahrenheit on the left. And notice the difference between the freezing point of water and the boiling point of water. Celsius and Kelvin both have it set up so that it's exactly 100 degrees, one of those powers of 10, which is super, super cool. And Fahrenheit, though, the difference is 180. Now, the way that the Fahrenheit scale started, they were trying to get the coldest temperature to the boiling point of water, blah, blah, blah. So at the time, I understand that made sense for the Fahrenheit. But Celsius, when he came along, he said, hey, 0 is going to be freezing point of water and 100 degrees Celsius is boiling, which is cool. And then Kelvin came along. Kelvin needed a temperature where at that temperature, all matter stopped moving. 0 Kelvin, which I mentioned earlier. So that's why 0 Kelvin is important. And then 273.15 is the freezing point of water. And 373.15 is the boiling point of water. So the difference being 100 degrees is super, super important. And it makes converting Celsius to Kelvin and Kelvin to Celsius super easy. It is difficult to go from Fahrenheit to Celsius, or even worse, Fahrenheit to Kelvin. You can do it, definitely, but it's kind of a trip. A Kelvin, a difference of 1 Kelvin is equal to a difference of 1 degree Celsius. And that's going to have some pretty serious implications for what's going on. So again, it's not that you can't use Fahrenheit, it's just it's more awkward. The math is harder, et cetera, et cetera. So that's why scientists usually use Celsius and Kelvin. We'll usually measure Celsius in the lab, and with calculations, we'll usually use Kelvin. So again, no degree symbols for Kelvin. But another thing is that Kelvin for chemists is never going to be a negative number, all right? Because if at 0 Kelvin all matter stops, you can't go below 0 Kelvin. That doesn't make any sense. So for us, Kelvin temperatures will never be negative. Celsius and Fahrenheit can be both positive and negative, but Kelvin's never going to be negative. Now, if you look at really hardcore advanced physics theories, once in a while they talk about negative Kelvin temperatures, and that's really, really cool stuff, by the way. Literally cold. No. All right, cracking myself up. Profat back on. Anyway, Kelvin temperatures in chemistry will never be negative numbers because it doesn't make any sense. You might see some negative Kelvins in advanced physics courses, but in chemistry, Kelvin is always going to be a positive number, which is kind of cool when you're calculating. Celsius can be negative, but not Kelvin. And again, if you can try to avoid using the degree symbol in Kelvin, that's also pretty awesome. So you might be asking yourself, how do I convert Celsius to Kelvin or Kelvin to Celsius, Dr. Russell? Great question, random student. So to convert Celsius to Kelvin, or as we'll see, Kelvin to Celsius, you need to know 273.15. And this is a number you just have to memorize. That's all there is to it, because we're going to use this over and over and over again. Now, remembering that Celsius temperatures can be negative, but Kelvin temperatures will never be negative, you add 273.15 to the Celsius to get the Kelvin. So Celsius temperatures, which can be negative, can be turned into positive kelvins by adding 273.15. Likewise, if you have a Kelvin temperature you want to convert to Celsius, you take that Kelvin temperature and subtract 273.15 to get the Celsius temperature. Here are just some examples. 37 degrees Celsius is roughly the body temperature of the body. If you wanted to figure that out in Kelvin, you'd add 273.15 to it to get 310.2 Kelvin. Now, mathematically, it comes out to be 310.15, and I'm rounding to 310.2 Kelvin. I'll talk about why I'm doing this later, but for right now, just realize there's a reason for having the two numbers there. So the little number, the italicized number, is what you get in the calculator. The black number is the number you should actually report, and we'll talk about that soon. Liquid nitrogen is a very cold liquid. It's pretty cool, used in movies sometimes. 77 Kelvin is the temperature of liquid nitrogen. And if you wanted to figure out what that is in Celsius, you would subtract 273.15 from it to get minus 196 degrees Celsius. So again, Kelvin temperatures should never be negative, but Celsius temperatures can be negative. So that's why we're doing it. If you have to use Fahrenheit, and it's sometimes you just have to, and it's also nice to make connections with what you're hearing in the actual world versus what we're doing in the lab, you can do it. You take the Celsius temperature and you multiply by 1.8 or 9/5, and you add 32 to it. So if you have to convert Celsius to Fahrenheit or turn Fahrenheit to Celsius, this is the equation you'd want to use. So if we wanted to turn the liquid helium temperature of 4.2 Kelvin into Fahrenheit, what I would do is I would first take the Kelvin temperature, subtract 273.15 from it to get minus 269.0 Celsius. So that's the Celsius temperature for liquid helium. Then if I wanted that temperature in Fahrenheit, I would multiply 9/5 or 1.8 times minus 269.0. I would add 32, and you get minus 452.2 Fahrenheit, which is freaking cold. All right. 32 Fahrenheit is where ice begins to form if you're waiting for snow days at school. Not that I do that, of course. I'm a sophisticated teacher, but if I was to do it, anyway. So minus 452.2, we would definitely have a snow day. That's really, really cold and stuff. So anyway, so you could do this yourself with temperatures. You could take the Celsius, convert to Fahrenheit or whatever. So here's a problem you might see. Here are three temperatures on the Earth: 29 Celsius, 45 Fahrenheit, 256 Kelvin, and put them order of increasing temperature. So from the coldest to the hottest. All right. So what you'd have to do here is convert all of them to a common temperature scale. And what I would probably do is I would convert them all to Celsius. All right. I would take the Kelvin temperature. I would subtract 273.15 from it to get the Celsius temperature. I would then take the Fahrenheit temperature, which is T degrees F. I would first subtract 32 from it, and then I would divide by 1.8 or 9/5 in order to get the Celsius temperature. And if you do all of that, you should see then the answer comes out to be D. 256 minus 273 gives you a negative temperature. So that would be a negative Celsius temperature would be the coldest, definitely. 45 Celsius minus 32, that would be about 13. I would then divide by 1.8. So that's going to be a pretty small number. It won't be negative, but it will be small in terms of Celsius. And then 29 Celsius would be the largest one. Anyway, I am going to try really hard to never make you do Fahrenheit, though, on actual quizzes and exams, but this is what you would do if you had to translate from one to the other. Volume is another property that has to be measured sometimes. And volume is the area that, or the space that a substance takes up in 3 dimensions. So length, width, and height, or X, Y, and Z axis. And what chemists usually use for volume are liters, which gets the symbol capital L. Don't use little l, use a capital L. Milliliters, which is little m, big L. And a centimeter cubed, which is centimeter to the 3rd power. And these are used a lot. Now, a milliliter and a centimeter cubed are the same thing. One equals the other. So if you see milliliters, you could cross it out and put centimeters cubed in there, or vice versa, and all the chemists would be really cool about that. And another unit that's used a lot is to convert milliliters to liters. So 1,000 milliliters would be 1 liter. You could also use 1,000 centimeters cubed equals 1 liter. Now, centimeters cubed seem weird, but centimeters cubed stem from the fact that it's length times width times height. So if you had 1 centimeter, a cube that was 1 centimeter by 1 centimeter by 1 centimeter, the volume would be 1 centimeter times 1 centimeter times 1 centimeter, 1 centimeter cubed. So if you see a centimeter cubed and it's like freaking you out, don't let it freak you out, all right? Just literally write it centimeters times centimeters times centimeters, and that can be helpful. And a meters cubed would be meters times meters times meters, stuff like that. So we'll talk about these, but again, chemists use liters, milliliters, and centimeters cubed almost all the time. We don't use the decimeters cubed and those kind of things very often. Oh boy. The American units, the imperial system units, are just totally messed up, in my opinion, when it comes to volume. There's pints and cups and quarts and teaspoons and tablespoons, and oh boy. You know, I've tried to cook things and I'm like, really? It's got all these weird things. It would be so simple if they just used milliliters. But anyway, good old Dr. Strange there is showing you how there's, I think it's 8 pints per gallon and 4 quarts per gallon and blah, blah, blah. It's very mesmerizing. We don't need to worry about that. All right. In chemistry, it's just milliliters, liters, and centimeters cubed. And if you know that there's 1,000 milliliters or 1,000 centimeters cubed in a liter, honestly, you're good to go and you won't have to use those things. But again, we live in this world, so if you have to, you can totally do it too. No worries. The density of a substance is important. You can actually separate substances by their differences in density. So density is a relationship between the mass of an object and the volume it occupies. So the mass is usually in grams, and the volume will be milliliters or centimeters cubed. So you can see on the right-hand side there, gold has a density of 19.3 grams per centimeter cubed. The mass, so in 1 centimeter cubed or 1 milliliter, remember they're the same thing, you have 19.3 grams of gold. Now mercury, the lower part there, is 13.6 grams per centimeter cubed. So that means in a centimeter cubed or a milliliter, you're going to have 13.6 grams of mercury. So the density of the two is different. Now substances will a lot of times align themselves. The more dense things go to the bottom and the less dense things go to the top. They call it superposition sometimes, and that can be very useful when you want to separate out different substances. So here's a video showing Diet Pepsi versus Pepsi in water.
First, the can of Pepsi is dropped into the water. Note that the can sinks. Now the can of Diet Pepsi is dropped into the water. Note that the can floats. What causes the difference in densities? Pepsi contains sugar and Diet Pepsi contains aspartame. Sugar solutions are more dense than aspartame solutions.
Aspartame, which is also known as NutraSweet, is used in a lot of diet drinks, and it has a different relationship with the water in the Diet Pepsi than sugar does with the water in regular Pepsi. So you can actually separate them out using that system. So here's an example of a problem you might see. Let's say that you had polypropylene rope, which is used when you're water skiing. You hold on to that rope and stuff as the boat pulls you around. Polypropylene floats on water, and soda bottle plastic, which is made from a compound called terephthalate like polymer, you don't need to worry about that, sinks in water. So the question is, what's the order of increasing density, i.e. which one is the most dense, which one is the less dense? Well, the less dense thing will be usually on the top, and the most dense thing will be on the bottom. So because the rope floats, that's going to be the least dense, the polypropylene. Water would be in the middle, and then the most dense, the part that sinks, would be that soda bottle plastic. So answer B here would be the right way. Because one floats and the other one sinks, that's why they have different densities. You can use this to separate out plastics while recycling, which is kind of a cool concept that's used sometimes. Here's a problem where we can actually use density in some interesting ways. Let's say that we have a piece of copper. It has a mass of 57.54 grams, and our piece of copper is rectangular. It's 9.36 centimeters long, it's 7.23 centimeters wide, and it's 0.95 millimeters thick, so not very thick. But let's say we wanted to calculate then the density of the copper, and density is usually in grams per centimeter cubed or grams per milliliter, either way. Solids are usually measured in centimeters cubed for volume, and liquids usually have milliliters, but you can interchange them if you want to. That's not written in stone, but that's what usually happens. Well, no problem. What we're going to do here, we're going to take the mass, the 57.54 grams, that'll be our numerator, and in the denominator, the bottom, we want the volume. And volume here will be centimeters times centimeters times centimeters, but one of our units right now is in millimeters. So the first thing we need to do is convert the millimeters into centimeters. And earlier I showed a thing where there was 10 millimeters per centimeter, so 0.95 millimeters would be 0.095 centimeters. And now that we have that unit in centimeters, we can multiply those 3 centimeter values by each other. So length times width times height, essentially. They have to all be the same unit, though, because we want centimeters cubed out of it. If we left it in millimeters, first of all, the answer would be different, and the units would be centimeters squared times millimeters, which is kind of awkward. So we want to have just centimeters cubed for volume, and that comes out to be 6.4. And again, I'll talk about why we're rounding them here in a little bit. And then finally, the density of the copper would be mass in grams over volume in centimeters cubed. That's going to come out to be 9.0 grams per centimeter cubed. And this is how they could figure out the density of this metal. And you could do this for any metal. It's a nice way to sometimes confirm if you have the right metal or not. You can look for the right density. Pretty cool. Here's another kind of problem. This one is based around what's called the Archimedes principle. And Archimedes was pretty clever. He was a scientist that figured out, hey, water displacement would be a great way to find the volume of an unknown solid. So for example, in this problem, we have a solid, but unlike the last problem, we don't have a nice length, width, and height. All right, a lot of solids come kind of messy. If you ever looked at rocks outside, that's kind of how this works. So the question is here, we've got some kind of piece of metal. It's 33.2 grams, and that you can measure on a scale, so that's not a problem. But we don't know the volume, and we don't have a nice length, width, and height. So what we're doing is we're starting with 10 centimeters cubed of water on the left, and when you add the metal in, you can see how the metal plus water combination goes up to 22.3 centimeters cubed. So the metal displaces the volume from 10 to 22.3 centimeters cubed. And in Archimedes' principle, then, you can take that final volume with both, subtract the volume of just the water to find the volume of your unknown metal. So in this case, the volume of the metal, we're not going to do length times width times height. We're going to do 22.3 minus 10 to get 12.3 centimeters cubed. That's the volume of the metal. And we have the mass of the metal. So the density of the metal, mass over volume, 33.2 divided by a total of 12.3, the density comes out to be 2.70 grams per centimeter cubed. And if you look at that table there, then it's going to be answer E. We have a piece of aluminum. Woohoo! Supposedly Archimedes figured this out while in the bathtub. I don't know if this is true or not, but Archimedes sat in there and he realized that he displaced the water, and they can use this then for finding fake gold. Apparently the king, wherever Archimedes was living, was having a problem, fake gold versus real gold. People were selling fake gold as real gold, and of course that's a drag. So Archimedes realized that you could use this displacement method. Fake gold is nowhere near as dense as real gold, so it would have a different effect on the water, and Archimedes saved the day. All elements have a different density, as well as compounds, etc., etc. This is a graph just kind of showing some of the densities of them. You can see that the kind of yellow-orange ones there, most of those are pretty small densities. Then you start getting into some bigger ones, and then finally some of them have very, very large densities. Now, some of these densities I'm a little skeptical. So in the kind of lower right-hand corner, there's AT, astatine. It claims it has a big density. I'm a little skeptical of that value. But anyway, you at least get the idea that all elements have their own density, and compounds do as well. So it's not that the density is the best way to identify an element or compound, but it can be a useful tool when people are analyzing compounds they don't know what it is, stuff like that. Here's another kind of problem you might see. In this case, we have mercury. Now, mercury, if you remember from earlier, is a liquid at room temperature and pressure. So in this case, we have 95 milliliters of mercury, all right, because this is a liquid. And again, liquids are usually recorded in milliliters, but if you wish to call it centimeters cubed, that's fine too. Well, mercury has a density of 13.6 grams per centimeter cubed. What is the mass of mercury? And if you want, you can record it in grams, or if you want to go to pounds, you can too. This is an example of what's called dimensional analysis, which sometimes is called factor label, has different names, but it's when you want to convert one kind of unit into another. And in this problem, we want to convert milliliters, our starting unit, into either grams or pounds, our ending unit. And if you do that, you need a conversion factor or a factor in order to convert one from the other. So we're going to use the 13.6. That's a relationship between the grams mass of the object and the centimeters cubed or volume of the object, which is really cool. And again, along the way, remember that milliliters and centimeters cubed, same thing. If you remember that a centimeter cubed and a milliliter are the same, you can use dimensional analysis then to calculate the mass. So 95 centimeters cubed times the density, 13.6 grams per centimeter cubed. You can see on there what we're doing. The initial unit is canceling out. Now in math, 5 over 5 equals 1, or x over x equals 1. Well, in this type of world, a centimeter cubed on the top cancels a centimeter cubed on the bottom. So centimeters cubed over centimeters cubed also equals 1, if you will. That means the centimeters cubed unit is gone. And the unit that's left, grams, is what's going to happen. So this comes out to be 1.3 times 10 to the third grams, or about 1,300 grams. I'll talk about why we're rounding here in a little bit. So that would be the mass of the mercury in grams. And if you wanted to know it in pounds for whatever reason, no problem. We can now use the conversion of 454 grams equals 1 pound. So again, notice here how in these factor label, you're starting with one type of unit and converting to another. In the last one, we went centimeters cubed to grams. In this one, we're going to go grams to pounds. So we'll take the grams, we'll use the conversion of 1 pound over 454 grams. You can see how grams on the top cancels grams on the bottom. In your calculator, you'd go 1.3 times 10 to the third divided by 454, and you'd end up with 2.9 pounds of mercury. Okay, so about this time, you're probably wondering why the heck I'm rounding up some numbers and what exactly is happening. So we need to talk in this part now about how measurements can be uncertain, and also what it means to have accuracy and precision when it comes to a measurement. And these things are kind of fundamental, but it's probably something maybe that you haven't thought about before, so let's just go through it. And counting is really the only kind of measurement that's free from uncertainty. So for example, if you have a bunch of dimes on your table, you can count them 1, 2, 3, 4, 5. You can get exact values that way, which is really, really cool. But most of the time, when you measure things, you don't have exact values, which is just crazy. So if you have things from counting, cool. But if you don't have measurements from counting, there's always going to be some uncertainty. They're not going to be exact values. And we'll see this in the lab. When you measure, for example, mass, we're using electronic scales. And, oh, that's going to be super accurate. Well, no. The mass scales themselves actually go up and down a little bit. We'll see this. And when you measure volume, like, do you know exactly what value you have? So uncertainty is almost a given when it comes to measurements. All right, unless you're counting and you have measurable amounts that won't take you a lifetime to count, then you have to figure out there's going to be some uncertainty in it. And the question of uncertainty then leads to precision. All right, will the results that you make more than one time, will they give you the same number? So for example, if you have like a bunch of dimes you're counting, will your friend, if they count the same thing, will they get the same number? And will your friend's friend get the same number? Now, again, when you're counting, it's usually not a big deal. But boy, if you're taking mass measurements and volume, there's almost always a little bit of uncertainty. So precision just means that multiple measured values are relatively close to each other. And accurate measurements means that you did a good job. So if you knew there were exactly 50 dimes and you measured 50 dimes, cool, you're very accurate. On the other hand, if you get 49 dimes when there's 50 or 51, that's not accurate. That would be a little inaccurate and stuff. So chemists think about precision and accuracy all the time. Like, are the measurements fairly close to each other? Are they repeatable, which is really important? And they also wonder about the accuracy. And if you know the accuracy, you have something to compare it to. And if you don't have accuracy, then you have to think about, is this a reasonable value? So significant figures, which are abbreviated as sig figs a lot, is just a great way to figure out how accurate a value can be reported. All right. And in this value, probably you're going to have one uncertain value and the other ones will be good values. All right. So if you make a measurement, say 3.14 meters, all right, usually what happens is the first digits are considered accurate. All right. They're excellent measurements. But the last one would be uncertain. So in 3.14, the 3 and the 0.1, those are good. All right. I think everybody would measure those. But the final one, the 0.14, the 4 of that number, that one maybe people would have different. So if you looked at it, maybe you'd measure 3.13. And if your friend measurement, maybe they'd measure 3.15. So in chemistry, sig figs means that you've got a lot of confidence in the first numbers, but maybe that last one, there's a little uncertainty. So here's an example showing accuracy and precision a little bit. So this is an example of a dartboard, and let's say that you're throwing the darts, all right? And we'll consider that the blue dot in the middle would represent an accurate throw, all right? So the first time you throw, you're out there and stuff, and boy, you're a dart master and you throw it right there. Sweet, all 3 darts right in the middle. So first of all, this would be considered very accurate. You want to be in the blue dot, and all of them are, which is really cool. This one is also considered precise because all 3 measurements were at the same value. They were all very close to each other, all right? So this one is both accurate and precise. Accurate because you're in the middle, which is where you want to be, and precise because all 3 darts are in the same area. However, after a few root beers, you decide to throw the darts again. And this time you're a little sugared out, so you throw them, but oh man, not even close to the blue dot. All right. However, you had enough control that all 3 of the darts were relatively close to each other. So this would be considered not a very accurate throw because you're not even somewhat close to the blue dot, but you still had enough control that you had a high precision. And this happens a lot in lab. Like you'll make 3 measurements and they're all really close to each other and you're feeling really good. Like, yeah, I did a good job. So your precision was definitely good. However, you may or may not be accurate. Like maybe there was a fundamental flaw in your experiment that prevented you from getting the blue target in the middle. So if you have measurements which are close to each other, they're at least precise, which is cool, but they may or may not be accurate. Finally, after you have a few more root beers and you're all sugared out, you decide to throw them again, but this time you're so jittery that you can't throw anything to, you're amazing you're even on the dartboard, let's put it that way. Now, these 3 darts are not close to each other, so this is poor precision, all right? This is not a very good job. You were unable to get repeatable results, and you're also a long ways from the dot in the middle, so you're not very accurate. So these are the things that scientists think about and worry about sometimes too. You'd ideally like to have them at least be precise. You want them to be close to each other. That shows that you're paying attention, you're doing a good job, all that stuff. However, you'd also like them to be accurate. You want them to be where they're supposed to be in the middle and not, for example, in the upper right-hand corner or something like that. And you definitely, above all else, should not stand next to the dartboard when you're having lots of drinks, because you never know what people will do. That's just stupid to show. But anyway, scientists ideally wish for both high accuracy and high precision. And most of the time, it's not, you can do high precision if you're paying attention, unless the experiment is weird. And you ideally want high accuracy, but you always have to be worried about this and stuff, because if you don't know what an accurate value is, that could be trouble. So we'll talk about this as we go through the course. But just think about now this difference between accuracy and precision. And again, good scientists want both, and you can hopefully at least get good precision. Here's an example of some actual values now, all right? We're measuring the milliliters of cough medicine, and we're delivering them in a 296 milliliter dispenser, all right? And you can see here that the first person to do it got the first first column of values, the second one got the second value, and the third one got the third one. So in the first one, you can see that all of those measurements in the first column there were about 283, 284 milliliters. 283.3, 284.1, 283.9, etc. So all of those measurements are pretty close to each other. That would say that they're very precise. But this person maybe didn't fill it up to 296. I don't know what happened, but they aren't very accurate. All right. They got good precision, so they were paying attention, but something in their technique must have prevented them from getting the 296 values. All right. Now, in dispenser number 2, when they went up there, they had 298, 294, 296, etc. So their values were certainly closer to 296. I would consider that to be more accurate, but the numbers are kind of all over the place. Like you have a high of 298 and a low of 293. So that's a pretty big plus or minus. That's not very high precision. The values were kind of far off. Now, the third person, dispenser number 3, to do this, all of their values were very close to 296, all right? 296.1, 296.0, et cetera, et cetera. So those were both accurate and precise. They were both they were all what they should be, about 296, and the values were all very close to each other, so they had high precision. And this is just a factor of science, what happens when you start measuring things, and you just try and do the best job you can do. Accuracy, when you want to measure it, is usually recorded as percent error, all right? And we'll see some examples of percent error in lab. Well, precision is usually measured in terms of what's called a parts per thousand. And parts per thousand is literally a measure of precision. So if you want to see how accurate you have, you can do a percent error analysis. And if you want to see how precise you are, you can do parts per thousand. Now, you can always do parts per thousand analysis if you have 2 or more values, and it's not too hard of a thing to figure out. Accuracy, on the other hand, you do need to have the actual value of what you're measuring. And if you have that, then you can find percent error, i.e. how close your value is to the actual value, and then find it. And usually the smaller percent errors are more accurate. Here are just some kind of nerdy equations. We'll talk about these more in lab, but these are the ways that you can actually find the parts per thousand and the percent error. And in parts per thousand, what you want to do first is find the average deviation and then find the parts per thousand. And for percent error, again, you have to have the accepted value and then compare it to the experimental value. We're going to do more of this in lab. We'll definitely do a lot of parts per thousand and some percent errors as well. There's a website for parts per thousand that I have set up, mhchem.org/ppt. So if you're curious, you can check that out, watch the video, whatever you want to do. We'll do this more in lab, though, nothing to worry about right now. But I do want you to think about that as a good scientist, you should think about both the accuracy and the precision of your measurements. So in the lab, when you want to make a measurement, there's always going to be some uncertainty. So the question is, how the heck will you record the volume in this graduated cylinder in the picture? And if you look very carefully on the right there, you can see that most water-based samples have a meniscus, which is like a curve to them. And usually what you want to do is you want to record from the bottom of the meniscus. But what do you call this? All right. I think if you look at those lines on the side, you can go 15, 16, 17. The water is between the 17 and the 18 milliliter mark. But what do you call it? Do you call it 17 milliliters? Do you call it rounded up and say 18? I think it's 17.5, 17.41. I mean, what do you call it? So chemists have a set of values which are collectively put under the significant figures idea to talk about what it is. And usually what you want to do is you want to record the volume to one more place than you have the lines for. So like we said earlier, this particular measurement, we have at least 17 milliliters, and it's not 18, but it's more than 17. So what we would do is we would guesstimate, or estimate is a better word, I guess, estimate one more position beyond the lines. So we have lines to the whole milliliter. So 15, 16, 17, 18. That means we would estimate to the 10th. So I would probably say that this volume was 17.5 milliliters. The 0.5 is the uncertain part. Like maybe you would say 17.4, or your partner would say 17.6, and that's okay. That last part has a plus or minus associated to it. We're doing the best that we can. So significant figures is really important to us, but remember that all measurements, that last digit, unless you're counting, that last measurement is going to be uncertain. So what people do then is they always put one more additional estimated unit. Like there's units that they know, and then there's one that they don't know. And that last one is called the doubtful digit. It's uncertain. Now, hopefully it's like plus or minus 1, but honestly, it depends on the experiment, all right? And so usually plus or minus 1 is a good idea to start with, but it might be more and it might be less. Now, the total number of digits that are used to express these measurements are called the number of significant figures. And significant figures, a lot of times, is abbreviated sig figs. So both the number of sig figs is going to be important, and also where that uncertain or doubtful digit on the uncertain value is going to be. So for 65.07, that has 4 significant figures, 4 numbers, all right? And the doubtful digit, the one that's uncertain, will be that 7. So perhaps if you measured it, it would look 65.06 or 65.08, all right? That last one we're not feeling really good about. But the 6, 5, and 0 we are feeling good about, so 4 sig figs, the last one being the uncertain or doubtful digit. Now here's a number, 54.70318. That has a lot of sig figs to it. 5470318, 7 significant figures, 7 values, all right? And the last one is the one that you're feeling uncertain about. The 8 is the doubtful digit. So we're not sure about that one. But the other ones we're feeling pretty good about. It's just the last one. So our measurement technique definitely makes a factor. Someone used a much better scale for the last one than they did the first one, because the first one only had 4 sig figs. The last one there had 7 sig figs, so we have a better measurement. Now, when it comes to sig figs, we have to talk about zeros, because zeros are important. So, for example, it makes a big deal if you have $10 versus $100 or $1,000 for that matter. The zeros tell you how many you have, but zeros may or may not be part of a measurement, because you need to show the order, the power of the number, but you may not want to have the actual 0 be a sig fig. So if the 0 is in the middle of non-zero numbers, they always count as significant figures. So 69.08, 4 sig figs. If the numbers in the front of it are zeros, then probably they're what they call a placeholder. So the 0.0089, those first 3 zeros just show you where the actual number starts. The first digit is actually the 8 right there. You can think about 0.0089. If you were going to record it in scientific notation, you'd write it as 8.9 times 10 to the minus 3. So that means those first zeros are just showing you where to start your numbers. So this number has only 2 sig figs. And a quick and dirty way to figure these things out is just put them in scientific notation. All the initial zeros go away. 8.9 times 10 to the minus 3 would be your value. Only the 8 and the 9 are significant. First zeros usually don't count. Zeros after non-zero numbers get kind of tricky. If the 0 is after the decimal, it usually counts. And a way to think about it, 2.50. Chemists don't really want to waste a lot of time writing numbers down, so they would write that extra 0 there if it was meaningful, if it was a sig fig. So 2.50 has 3 sig figs. Likewise, 25.00, chemists would rather write 25, but they must have had the precision to the hundredths to 0.00, so that's why it's 25.00. So 25.00 has 4 sig figs. That's what's really important. So 2.50 would be plus or minus the hundredth, like you'd have 2.49 to 2.51. If you had only 2.5, then that precision would be at the tenths. You'd have 2.4 to 2.6. So it does make a big difference if the 0 is there. If the 0 is there and it's past the decimal, there was a reason for the chemist including it, and they usually count as sig figs. Before the decimal, though, zeros may or may not be helpful. And so, for example, 1500, if you wrote it as scientific notation, that would be 1.5 times 10 to the third. So those zeros and that doesn't count. But what if you had a number, for example, 1500, where you had plus or minus 1, like it would be 1499 to 1501. If those zeros are significant, you need to include a decimal placeholder, a dot or a period. So 1500 dot says that those zeros are significant. You have 4 sig figs. So 1500 dot would be 1499 to 1501. The precision would be at the 1 spot. On the other hand, 1500 without a dot would be plus or minus 100. You'd have 1400 to 1600. So pay attention to the dot. If the dot is there, it's there for a reason. That shows that the zeros are significant. Sometimes you have what are called exact conversions or definitions, and those have essentially infinite sig figs, i.e. don't worry about them. So for example, 60 seconds will always equal 1 minute. So even though 60 looks like a 1 sig fig number, you don't have to worry about that because 60 minutes is always 1 minute. All the metric conversions are exact conversions, like 10 millimeters will always equal a centimeter, and 1,000 millimeters will always equal a meter, stuff like that. So you don't worry about them. It's the same thing with like 4 quarters equals $1. You will never have 3 quarters equal $1 or 5 quarters equal $1. It's always 4 quarters. So definitions, if you see them have infinite sig figs, don't worry about it. And finally, I just want to say, this is something you got to study, practice, very important. As an instructor, I take off a lot of points for people not paying attention to sig figs, and it's really important in this very experimental field. So take some time, kind of go through the examples in the book and the other resources that I have in the companion and online to make sure that you've kind of got the sig fig thing down. It's very, very important. So here's some numbers, and the question is, do they all have the same number of sig figs, true or false? And at first you're like, give me a break, they don't. But if you look through them, 1,000 dot means that those zeros are significant. So that's 4 sig figs. And 9.730, the zeros after the decimal, lazy chemists don't want to write things that they don't have to. So that 0 is significant. That's the plus or minus part. You'd have 9.729 to 9.731, something like that. The third one there, 0.004270, if you write that in scientific notation, it would be 4.27 times 10 to the minus 3, but the chemist put a 0 at the end, must be a reason, because chemists don't want to do it otherwise, 4 sig figs, so you'd write that 4.270 times 10 to the minus 3, include the 0. And finally, the last one, the zeros are at the end, there's no dot, you could write that 2.998 times 10 to the 5th. All of those 4 digits are significant. Punchline, they all have the same number of sig figs. They all have 4 sig figs. So this is what's important to figure out how many sig figs there are in the number. That'll be really important for our math calculations coming up. Scientific notation, I'm hoping, is something that you know, but if you haven't seen it for a while or you don't remember, it's pretty chill. You can write really big or really small numbers using scientific notation, and you always want to write scientific notation as a number between 1 and 10 times power of 10 to a certain power. So let me just go through some examples. So 215 you would write as 2.15 times 10 to the second. You have a digit between 1 and 10, not more than 10, but between 1 and 10 to the left of the decimal and everything else to the right. And notice that we move the dot over 2 places to make it a 2.15. That 2 places to the left means 10 to the positive 2. So if you move the decimal to the left, it's a positive integer, like that one is right there. But you can also have small numbers. So if you had the 0.00000000156 and you wanted to write that as scientific notation, it would be 1.56, but we'd have to move the decimal 8 places, all right? And that's where the -8 comes from. Excuse me. So in this case, 1.56 times 10 to the -8 would be 0.000000156. So just realize the small numbers have negative exponents. It doesn't mean they're negative numbers. They just have a negative exponent, and that's important. While the bigger numbers, greater than 1, will have positive exponents. It's really cool if you can figure out on your calculator how to convert from scientific notation to regular notation and vice versa. Your calculator can do all of this for you, and I highly encourage you to check this out. Every calculator is a little bit different. I will try to help you if I can. The math department can help you as well, but let the calculator do most of this if you can. Always use scientific notation while reporting numbers in lab, quizzes, exams, stuff like that. Don't show me really big numbers with tons of zeros or really small numbers with lots of zeros. I will not count your zeros. All right, I have better things to do. So if your number is, say, above 1,000 or less than 0.001, you should be using scientific notation, definitely. And so knowing how to go back and forth is cool. Also, don't use the engineering notation, which would be, for example, on 215, that would be 21.5 times 10 to the first. I don't know who uses that. I don't want you to use it. I want you to use proper scientific notation. So pay attention to it. I'm hoping it's a pretty chill subject, but if you don't know about this as much, I do have some handouts and some things to help you with it too. Calculators are obviously going to be a tool we're going to use and stuff, but sometimes the calculators will give numbers that are either too big or too small. And so large numbers and stuff, especially that you get from calculators, have to be rounded off to a smaller number, and you only want to keep the significant figures. So knowing when to cut a number off is important. So when you figure out how many numbers to keep, you want to look at the first digit to be dropped to know what you need to do to round. So if the first digit you're going to drop is between 0 and 4, you just drop it and all remaining digits and leave the digit alone. On the other hand, if the first digit you want to drop is between 5 and 9, you want to round the number up by adding 1 to the digit to the left of the one you drop. And I'm sure that's as clear as mud. So for example, 2.4271, if you want to cut it off after the 4, you look at the first digit to be dropped, which is a 2. And 2 is between 0 and 4, so you leave it alone. You would just call it 2.4. But the next one, 4.5816, if you want to drop it after the 5, look at the first digit to be dropped, which is the 8. 8 is between 5 and 9, so you want to round up. So your 4.5 becomes 4.6 when you round it up to 2 sig figs. So again, look for the first digit to be dropped. And notice in the 2.4271, the second digit to be dropped would be a 7. And it might be like, oh yeah, I should round up. No. You only look at the first digit. Only look at the first one. So 2 is between 0 and 4. Leave it alone. Don't do anything. But 8 is between 5 and 9, so you'd round up. 4.5 becomes 4.6. Some other books use weird rules about a 5. If it's the first one we drop, you ignore those. We're just going to use 0 to 4 and 5 to 9 and be good to go. Let's round this number to 3 significant figures, all right? And there's lots of different numbers in there. So to 3 sig figs, you might go 0.00. There's 3 sig figs. 3 is the first digit drop. Leave it alone, 0.00. Not quite that simple because the first significant figure is the 3. Like in scientific notation, this would be 3.0350 times 10 to the minus 3. So start counting at the first 3 sig figs. You'd have 3, 0, and 3. Those would be the 3 sig figs. But this has a 5 and a 0 after it. So to figure out if you need to round, you look at the first digit to be dropped. First digit to be dropped is a 5. 5 is between 5 and 9, so we'll round up. So the best answer here, 0.00304. Round it up. If it's a 5, between 5 and 9, round up. If it was between 0 and 4, just leave it alone. Multiplying and dividing is what we'll do most of the time in chemistry. And you'll multiply and divide like normal, but the answer cannot have more sig figs than either of the original numbers. So let's say that you were analyzing your car's performance and you traveled 278 miles and took 11.70 gallons of gas. Well, you calculate in your calculator and it comes out to be 23.76068, etc., etc., etc. To figure out sig figs here, the top number is 3 sig figs. The bottom number, 11.70, which has a 0, which counts, by the way, 4 sig figs. So when you multiply and divide, the answer has to have the fewest number of sig figs. So 3 is less than 4. We're going to round that number to 3 sig figs. So 23.76, etc. We'll cut it off after the 7. The first digit to be dropped is a 6, and that's between 5 and 9. So we'll round up. 23.8 miles per gallon is what we would call this. And most of the time in chemistry, these are the kind of problems we're going to do. All right, multiply and divide. And the smaller number of sig figs goes forward. So sometimes I'll tell you to fight for your sig figs. That just means we want to keep reporting as many sig figs as possible. And if you can keep those sig figs going, it's usually better than if you don't have enough sig figs. Adding and subtracting is a little bit different than multiplying and dividing. It's not about the total number of sig figs, but it's about the doubtful digit. So remember, the doubtful digit is the last number. So for 3.18, it's the 8. That's the doubtful digit. That's the 100th spot, if you remember from math. But if we're adding to the 3.18, 0.01315, in that number, the 5, the last number, is the doubtful digit. That's the 100,000th spot. All right. So when you're adding those numbers up, the calculator will give you 3.19315. But the problem in chemistry and in science is that after the 8, we don't know those numbers. If they happen to all be zeros, then 3.19315 would be right. But what if they were 3.18999 or something like that, or 3.18111? All right, we would get different numbers. So we have no confidence in reporting anything past the 8. We have no confidence in reporting anything past the doubtful digit. So the final answer that you get, you have to cut it off at what I call the largest doubtful digit. It's the last number that we have confidence in. And 3.18, that means the 100th spot is where we're going to cut it off. So we would call this 3.19. The 3, 1, and 5 that the calculator gives us, we have no confidence in those values because we don't know what's to the right of the 8, all right? And this is the joy of experimental science. You can only go with the values that you're given. So even though the 0.01315 had a lot more digits in it, we have no confidence in how to add that to 3.18, so we cut it off at 3.19. So doubtful digit is important when you add and subtract. And this is very important when it comes to temperature conversion, Celsius to Kelvin, Kelvin to Celsius. That's where we're going to use adding and subtracting in largest doubtful digits. Again, most of the time multiplying and dividing is the game to play, but sometimes, especially temperatures, that's when we're going to add and subtract, and you've got to remember the doubtful digit. So conversion factors are going to be really important in converting one thing for the other. Some of them are absolute, some of them are based on sig figs. But the important thing to remember is that if I said that there's 2.54 centimeters in an inch, there's a lot of different ways you can write it. You could write it 2.54 centimeters equals 1 inch. You could also write it 2.54 centimeters per 1 inch, or 1 inch per 2.54 centimeters. These conversion factors you can flip up and down. Numerators and denominators can be flipped, and you use what's right for you. Most of the time, conversion factors will follow sig fig rules, like densities and molar masses and stuff we'll talk about later, but there are a lot of definitions that don't worry about sig figs. So for example, in the English world, 1 foot is exactly 12 inches, or the imperial unit. 60 seconds is exactly equal to 1 minute in our science world. All the metric conversions are those kind of things. Those are the things that you would ignore sig figs. But boy, most of the time when it comes to conversions, use sig figs and think about them as you do your math. So in this problem, if we wanted to turn 34 inches into centimeters, we have a conversion of 2.54 centimeters per inch. We could write that as 1 inch over 2.54 centimeters, but in this problem, we want to write 2.54 centimeters per 1 inch. And the reason you do that is you want, like we talked about earlier, you want to have one unit cancel the other. Though the starting unit cancels and the desired unit, centimeters, is the one left over. So you want to cancel out those inches, get just the centimeters left, and you will be good to go. And that's how a lot of these work. So you wouldn't want to use 1 inch on top and 2.54 centimeters on the bottom, because none of the inches would cancel out. You always want to have something cancel out before you get to your final unit. Sometimes you'll see a mass percentage in chemistry. This is another kind of analysis we'll use once in a while. So let's say we had a sample that was 30% lead and 70% oxygen. What usually this means is that in 100 grams of the substance, you'd have 30 grams of lead and 70 grams of oxygen. And that's the way that we'll usually use these kind of things. This is a mass percentage, so that means grams, all right? So in 100 grams, you'd have 30 grams of lead, 70 grams of oxygen. But you don't have to think about it as 100 grams. You could also think about it as 1 gram. 1 gram would be 0.3 grams of lead and 0.70 grams of oxygen. It's your call, all right? But that's normally what I will talk about is if we had 100 grams, then those percentage numbers just equal the grams of whatever we're looking at. And we're going to see that mass percentages can be really helpful to chemists as we try and find formulas. This is an example of a penicillin compound, penicillin F. It's 53.829% carbon. And the question is how much carbon is in 75 grams of the penicillin. In the lower right-hand corner, that's the structure of penicillin. We'll talk more about how to interpret that in a later lecture, but for right now, we just want to find out how much carbon, how many grams of carbon is in 75 grams of the penicillin. So what you would do is you'd use that mass percentage. That means 53.829 grams of carbon in 100 grams of the penicillin. So what you can do then is set that up. You start with the penicillin, 53.829 grams of carbon in 100 grams penicillin, and you can see how the penicillin F in the top cancels this penicillin F in the bottom. So there's no more grams of penicillin, we only have grams of carbon. Now your calculator will give you 40.37175, which is great. However, because of the 75 number, we have only 2 sig figs. 53.829 has 5 sig figs, but we want to have the fewer sig figs go forward. So we're going to cut this off after the 0. The first digit to be dropped is the 3, so that means we leave it alone. We'll call it 40, but don't forget the dot, because a 40 without the dot looks like a 1 sig fig number. 40 with a dot means 39 to 41, plus or minus 1. 40 without a dot would be plus or minus 10, so it would be 30 to 50. So we're going to maintain the 2 sig figs by putting the little dot right there. Chemistry, gotta love it. Once in a while, a volume percentage is used. So like in 100 milliliters, you'd have 53 milliliters of carbon or something like that. Not as common, all right? And especially not in our classes. Most of the time in this class, you can just assume that they are mass percentages based on grams, all right? So if you see percentages, unless I tell you otherwise, just assume that they're grams based, not milliliters or something like that. Okay, so that's the end of Chapter 1, and I sure appreciate you being here with me. As you think about Chapter 1, here's some more information and some resources to help you study. So first of all, in the Chemistry 221 website, or in the companion, there's what they call a study guide. And a study guide is a bulleted list of concepts from Chapter 1, which I think are pretty important. And you can just kind of look through those, make sure that you feel okay about them. If you see something that's weird, you might look back in the notes or in the textbook and stuff to see what's going on. A concept guide is a series of worked problems from Chapter 1, and it'll show you, for example, how to do sig figs with multiplying, sig figs with dividing, density stuff, jazz like that. Those are kind of fun, and you can look through them and just see some of the problems. You'll say, oh yeah, that makes sense. But if you see something that doesn't make sense, follow the example a little bit closer then to make sure you're good. Now also, I have what I call Chapter Guide 0, which is a math concept guide. All of you are coming from a different perspective and background. If you haven't seen some of these math things before, check out the concept guides for the math section, Chapter Guide 0, because it'll go through some examples of how to multiply and divide and exponents and scientific notation, stuff like that. Now, I won't show them today, but after this slide, if you look at the regular lecture notes, I do have a series of important equations from Chapter 1, which will show you the things I think are kind of important. And following that, I do have some problems that are kind of example problems from Chapter 1. And the one slide has the questions, and the next slide has the answer to the questions. So if you test yourself, you can then make sure that you're good to go with Chapter 1, and you should be happening no problem. All right, if you have any questions on any of this, please let me know. I'm more than happy to answer your questions. Thank you again for being here. Have a wonderful day.